1, 2, 1, 1. Does that work? Yeah. 1, 1, 2. This last time people on Zoom were saying that if I go too far from the laptop, they won't hear. So I'm thinking of setting this a bit higher volume. Is that okay? Like this? Okay. Okay, shall we get started? How was it? Yeah, so I hope everyone submitted the assignment, and we have now released a second one. So that is due in almost 2 weeks. So you still have time to work on it. So you'll have if you have any questions, do come to our office hours. So I have an office hour today, and also one of my TAs also have another office hour. So post on Piazza, on our forums, and let's get started. So I don't have my clicker with me today, but I'll stay here with the laptop. Last time we started talking a bit about what is a general idea of a loss function. How do we define, in more general terms, a loss function? And we saw, for example, for least squares, this is how a loss function looks like, which is a squares of the error terms between the predictions and the labels. For logistic regression, this is the loss function that we have, and this is a case of a binary problem where y has only +1 or -1. And we can also write it like this. So basically, we can take a sum over all the data points, and this again assumes independence across data points. But we can also write it like this, and this is also called empirical risk minimization. So in other types of literatures in ML, and we started discussing that the way we can optimize it is using gradient descent. So we have our surface, our loss function here. This is in 1 dimension, and we start from an initial guess here, and we basically take small steps 1 by 1 up until we slowly start to minimize this function up until we get to an optimum value here, m. So this and how we get to, how we know the direction that we have to go, for example, left, is because of the gradient. We compute the gradient at this particular point, location. The gradient of the function, or the derivative, you might have heard in high school as a derivative. So that's the gradient. It's, if you have a function like this, the gradient will be a line that touches in one single point the function. So that one will tell us, the gradient will tell us the direction of most increase. So to decrease it, we have to take the negative. We have to go the other way around, so in the negative direction. So this is what we mean here by negative gradient. We have to go the other way. Does it make sense? Any questions? Do we always converge to an optimum? Maybe a local one. So this is detail a bit more. Why is it? Why could it be a local one? You have a saddle point, yeah. What if the function has multiple local minimas? The function could be, so in that case, this is, for example, this is a convex function, but the function that might not be convex, our loss function might not be convex, and then it might have multiple local minima. So we will just converge to one of them. Can it be that we don't end up here, that we maybe go on the other side, we overshoot? Can that happen? Mm-hmm. Yeah? When does that happen?
Well, we're taking 2 large steps.
2 large steps, yes. So we'll talk here shortly how when we take the gradient, we take a step size, and if that step size is too large, we will overshoot. So we will kind of like end up on this side, and then we might kind of come back, and we will just jump back and forth between left and right. So we never really converge to the actual point if the step size is too large. So this is the general idea of gradient descent. So we somehow take small steps up until we reach convergence. And how and a particular variant of gradient descent is called stochastic gradient descent. And here for stochastic gradient descent, the key idea is that instead of taking all the data set at once, we just look at one single pair. And so for example, we randomly shuffle our data, x and y, and we take one pair of x and y's from this randomly. And we compute the gradient of the loss function with respect to our data point, x and y here. And then we take a step. We update our parameters, theta, by taking a step in using the gradient. So we start from the current estimate of our parameters, and then we subtract this gradient, which is calculated, times the particular step size. This tells us how big of a step do we take. We take small steps or much larger steps. So it's an iterative procedure, and we do the same thing, and we repeat until convergence. We take then a different data point, a different person that we, for example, like in the data set, we run their gradients and so on, and we keep doing this until we hopefully converge. So let's do one quick example of stochastic gradient descent. So for example, if we have one data point x, which has 1 and 2, so this is a data point that has 2 features, and y is a label which is 5. So this is, again, we're talking about a regression problem. Our parameters theta are initially 1, 1. The squared error on this example is this, which is So this is where we have theta. So we have theta, which we multiply by x. So x is 1 and 2. So we have 1 times theta 0 plus 2 times theta 1, minus 5 minus our label y to the power of 2. So this is a squared error. So this, if you do this, if you multiply this, this will be equal to 4. So the contribution to j of theta is 2. So basically, this is the case is 2 instead of 4 because we generally take a half. We do a half of those squared errors, and this is mostly because for it gives the derivations a bit nicer. It basically simplifies a bit the derivation, but that constant doesn't matter too much. The scaling constant. It just makes, because when we take the derivative afterwards, we this exponent from the derivative cancels out with this half. That's why. So we do that, and so this is our loss function. So then, what do? We take the gradient, right? So we take the gradient with respect to the two parameters, theta 0 and theta 1. And this is so this is our function. The gradient with respect to theta 0 is gradient of f of x squared is 2 times f of x times f of x prime, the derivative of f of x. Yeah. So this is what happens here. So the exponent comes in the front. It cancels out with 2. We get the same function times 1, and here this 1 is the derivative of this parentheses with respect to theta 0. It's from the chain rule basically. So this is basically, or there's many properties. You can also apply the derivative of a function and so on. There's many rules you can apply, but this is equals to minus 2. So if and this is because we replace, of course, theta 0 and theta 1 with our initial estimate 1, 1, and that's why we get minus 2. And the same thing for theta 1, and we get minus 4. We just multiply by 2 here. That's why. So then if we take a step size of 1 over 20, our update to theta would be theta, the original theta, which is 1, 1, minus 120 times the gradient of this of our function of our function with respect to theta. But this is we're talking about 2D. So this will be, these are vectors. This is a vector with 2 elements. This is a vector with 2 elements. So from theta equals 1, 1, we subtract this. So now we get parameters 1.1 and 1.2. Yes, question?
Why do we use step size 1 over 20?
This is a set a priori. You predefine it when before you start the gradient, the algorithm. You define a step size. So and kind of you can set it to be. You kind of use your intuition to set a reasonable step size based on the problem and the loss function. People try out different step sizes, and then you can run the algorithm with many step sizes and see which one works better, things like that. But it's set a beforehand. Yeah. So look what happened. So what happened is that from our initial estimate of 1, 1, now we moved to 1.1, 1.2. So and if I remember correctly, for this particular solution, the actual optimum is achieved as a 1, 2 for this particular problem. So somehow by going in, so you see if this particular point gets closer to 0.1, 2, which is not written on the slides, but it's our solution for this problem, if I remember correctly off the top of my head. So we're kind of getting closer to the solution basically of the problem, and if we do this again and again, we'll hopefully reach that solution. Any other questions about SGD? Let me show you an example. So this is a GIF. So here we have only one theta. Like our vector of parameters is just one parameter. It's literally 1. So our model here, you see, is we have a data set of points, of blue points, and then if I can find the cursor, yeah, here, and then our line is just y equals x times p. So p is our parameter here in this particular setting. and it's only one parameter, so it's 1D instead of 2D. So look how this is our loss function with squared errors, and look how we start initially from here, and we take several steps up until convergence, and how our model basically gets closer and closer to fitting the data as best as possible. So this is what is happening essentially. This is what we call in machine learning the parameter space. This is a space of all parameters of the model where we plot the loss function. So we're here in parameter space. We do not see in this particular graph, we do not see data points. These are just parameters of the model. There's no data points from a data set, from our data set. This plot has the data points from a data set. So in parameter space, we're finding the optimum. And in data space, our model changes so that it fits the data. So we have this basically these different models that converge to better and better. So that's does it make sense? A parameter space versus data space? Yeah, so you see these terms very often in literature, in ML literature. So people talk about parameter space. This is what it means. So now I wanted, like, for finishing up this particular section, I wanted us to go through a particular type of linear classifiers and show how we can actually use linear algebra to do a classification, like in particular like a regression for simple problems. So take this example. So here we have we're in a 2D space. So our inputs have two features, x1 and x2. So say I don't know. Age and income, for example, and you want to predict something else about the person. I don't know how they're going to vote. I don't know in the elections. So any example basically. So we have, for example, two classes of points, and we can derive different models or hypotheses. They called H because it's also called a hypothesis. This particular these particular models. We have a question. So we have a question from the audience. So in the previous plot, how do we plot this parameter space? How do we plot this? Yeah. So that's a very good question, actually. So you have to evaluate it at each point in the parameter space. So you see, normally if you just run gradient descent, you will not see the red line. You will not see it. You will only see these points. Imagine as if you do not see the red line, but you only see this point and then that point and that point up to convergence. So we actually don't. Yeah, you have to try all these parameters to actually be able to plot this in general for. Yeah.
What are the parameters that you have?
So the parameters for this scenario is just p. It's just one scalar here in this example. It's just a line. You see, this line. This is even simpler. This is not even a. This is a line that always has to go through origin. So it has only one parameter, which is this orientation, basically this p. So and p is so this line. Equation of this line is x times p. It's just that x times the inclination. The slope. Yes. So it doesn't even have a bias term, like an intercept sort of term. Because if it had an intercept that we had optimized, this would have been a 2D plot. This would have had an extra dimension, the parameter space. But in 1D, this is and I think it's really important because one thing I would want from you by the end of the course is to sort of develop an intuition and think more in parameter space. Actually, I want you to kind of like start developing this intuition, so to think more in these sort of terms, because it's easier to conceptualize all the algorithms in that space rather than in the data space. What is happening in the data space is literally this. Yeah, we're changing these models, or you can even have distributions, like probability distributions. We'll talk about later, where you'll have a Gaussian distribution that slowly moves to fit this data, for example. So we'll talk about that. So we go to more complex things, but in parameter space, again, we just have a point. So a single point here in parameter space maps to an entire model here, an entire model. This will be an n-dimensional space, like in n dimensions. And a single point represents the whole model completely. Yeah? So this is an example of a parameter space. This is also parameter space. No, sorry. This is a data space because we're talking about we're plotting the features here. We're not plotting the parameters of the function of these lines. But you see again we have different models and for example what you notice is that model H1 and H2 both can separate the data perfectly, essentially, at least the training data. And now what the question would be that which one of these models do you think would be more preferred, H1 and H2? So why H1?
Because when you project it onto it, you can see the two different sets.
That's very interesting. That's very interesting. Yes. And I also had H2. Why would H2 be preferred? You maximize the distance to the plane. Yeah. These distances, yes. This is really interesting. So both answers are correct. So essentially, it depends what you want. So sometimes you want your model to be as far away. So the boundary you want it to be as far away from the data points as possible because this is kind of like because maybe if you select this one, then it might be quite brittle. Like it might not be too robust. If you sample more data points, maybe you might end up some of them having actually being on the other side. So it might be brittle, not robust. I think that's kind of like one of the right terms. But what the advantage of this over H1, what it has is that if you project data points onto this dimension, they still preserve you still preserve the groupings basically quite well. So these will always group on this side, and these points will always group on this side if you project on H1. So this analysis is called linear discriminant analysis. So it's something like we will. I do not think we'll have time to go through that in the course, but it's a type of analysis that Fisher, like a statistician called Fisher, came up in the 20s. So it's quite well used, it's heavily used, and it's actually in our textbook of the course. But I don't know if we have time to go through it. But the idea would be that when you project, those two groups will be as separated as possible. So that is linear discriminant analysis. So really, really interesting, really nice. But right now we will focus for now for the next few slides on this one, on H2, on this idea of separating by having the having the boundary to be as far away from the data points as possible. So the goal here is to find a linear boundary again that separates the data points. And moreover, with this kind of boundary or model, we will be able to then predict points. So then if a new point ends up on this side of the line, on the part above, we'll make it as a plus. For example, it will be a +1, for example. And if it ends up on this side, it will be a -1, for example. We predict it as a -1. So how can we do that? How can we do such kind of model? So what we can do, we can take, so if you want a particular line like this, we take the vector W that is orthogonal to the line. So the W here is an orthogonal vector. And we can compute this basically. So for each of these x's, we can check if dot product between x and W is higher than a particular bias B. And if it's higher, then we can say it to be a plus, otherwise say it to be minus. This is like a linear classification with dot products basically between vectors. And you notice that for all these vectors x0, x1, x2 that are on this line, this will give you an equality. So x times W will be equal to B, to a bias B. And those will be the vectors on the line. Let's go into a bit more detail. Why is that the case? So what is the dot product? between vectors. It's on the slide. Yeah, so it's this one. So the dot product again between two vectors x and w is always the magnitude of x times the magnitude of w times the cosine between the vectors. But more intuitively, what it signifies is a projection of. It's literally, if you remember, like the dot product represents the projection of one vector onto the other vector and that distance. That's what it means. Well, so it's as if you project x onto w, and up to a scaling constant, but it's basically that. You can, and again, this is like a notation. What I'm trying to say is that generally when we do the product, we write it as x transpose times w, because this will be a row vector, this will be a column vector. But if you write it like this, then we can have two column vectors. But this would mean dot product, so it's the same thing. And we have this equation that each of these are equal to b. So this will give us points on the same line with this dot product equation. So in a sense, this space has two features. This means that a 2D classification has a 1D boundary. So always the boundary always has one dimension less than the dimension of the space. So then if we're talking about what is a boundary, what is a linear boundary in 3D? It's a plane, yes. In 4D, yeah, it'll be a three-dimensional space. So it's always like that. It's also called a hyperplane. So it's always that any linear boundary in an n-dimensional space will be an n-1 dimensional subspace, and we will call that the hyperplane. So does it make sense? I know it might be hard to visualize, but I think you'll get used to these, like kind of like these concepts slowly over the course. So we'll talk about n-dimensional spaces. Yeah. So more precisely, so when we talk about these lines, so you can define a line. The way we define a line is often by taking a vector that is orthogonal to it, and that's how we generally define a line. And it's the same, like sort of like equation in vector spaces. If you define the equation of a line, you take an orthogonal vector to that, and for example, any two vectors here, if you take r0 minus r1, then this will give you a line like that. The dot product between two orthogonal vectors is always 0. So then that's how you can define the equation of a line with also with vectors. So this, for example, is a distance between the origin to this particular to this point with w. And when you talk about this equation, x transpose x minus b. So you can write it in vector form like this. So this will be goes there. But you can also a trick that is often done in machine learning is that you can add this bias and put it in the weight vector. So then we extend the weight vector to have an extra element, the bias, and then you add an extra feature, an extra dummy feature to be just 1. So then this equation is exactly the same as this one. And this is now called a homogeneous system, because now we only have an extended w and an extended x, but we don't have any more bias. And now we have the dot product of two vectors now in 3D, for example, because there's an extra dummy variable that has to be greater than 0, and the boundary would be when this is 0. And again, the dot product of two vector, if it's 0, it always means they're orthogonal. Those two vectors are orthogonal. So that means that this equation here will give us, given a particular w, will give us a line of solutions for x, which is always orthogonal. So, and it passes through the origin now. The origin in this will be in 3D. So. Actually, this will be a plane in 3D. So because it's always, it will be a plane that passes through origin or a line. But exactly the same. So you give a vector, and you get a plane that is orthogonal to that particular vector. So one question is, does W have to be a unit vector? Do we have to normalize its magnitude to be 1? I hear shaking of head. No. No. Why is that?
As long as it's on the same line, it doesn't matter the magnitude.
Yeah, exactly. It doesn't have to be. One way you can think about it is that you can always scale them. You can always, if you scale W by a factor k, it's equivalent as scaling the W bias by a factor k. So then, like, this equation will give you the same solutions. We can just multiply this equation by k, and you get k times W times x minus k times b equals 0. So it's you can scale, as long as you scale both, you get the same. So these equations, this and that, if you scale by 2, they give you the exact same line. It doesn't matter. So this particular distance between the origin to the line, to this point x0, is basically the dot product between W and x0. So because W and x0 are, let's now call linear, this will be literally the magnitude of W times the magnitude of x0 divided by the magnitude of x of W. But since W times x is equal to b from our equation, then this also equals to b over W from our equation, because x0 is on the line. So we can use this to define the concept of a margin, where we basically take this form. So we move this to the other side, and we say W transpose x minus b divided by the norm of W is the margin, and we multiply by the label y. This is called the margin. This is sort of telling us the distance between another point xi from our linear boundary. This is how far away the xi is from our boundary. So it's super simple equations. We can use like linear equations to come up with these distances, and we're almost there. Yeah, we now we have a way to you see, now we have a way to predict, for example, the label of if we want to predict whether it's a plus, we simply do this equation, and we see if it's greater than 0, we assign it as a plus, otherwise as a minus on the other side. And we also compute the distances from this line. So and in general, for a classifier that there's a regular classifier that, for example, like just predicts discrete classes, then the margin is the distance from the decision boundary. Whereas for a scoring classifier, the margin, it would be the score. So for example, if you want to score, say, from your income, for example, you want to predict a credit score. Income and other things, you want to predict your credit score for your bank to get a loan. So you have a predictor for something like that. So then this particular margin, how far away you are from the boundary, would give you your credit score, essentially. Any questions? Okay. So the error in these models, when we want to compute the concept of an error, what we simply do is that we do our linear. So forget about this for now. Just look in the inside. So we do our linear transformation Wx minus b. We check if that is smaller or equal to smaller than 0 or bigger than 0. But then we we first multiply by the label, y. And what is happening here? So y can be either +1 or -1 in this particular situation. So if this particular value is for example, is negative, and y is negative, then it means we made the correct classification. We made, for example, like a -1 classification. So then this one will become positive. So there will be no error. If the idea is that if our prediction has a different sign from the label, then it means we made the wrong classification. So then their product will be negative. So y times our prediction will be negative when we made an error, because they'll have different signs. And when they have the same sign, either +1 or -1, that means we were correct. So to count the number of errors, we simply, what we do, we take an indicator function. This function indicates if this proposition inside the brackets is true or false. So if this was indeed smaller than or equal to 0, then we got an error. So then we count an error here, basically. If it was not, then we do not count it. So this is how we can define, for example, the error in one of these models. And then the objective function that we, based on this error, that we would minimize, is that we sum over all the possible, like over all our data points, n. We sum over all our data points, n. So this is to be xn and yn, and then we find, and we try to optimize it by finding the best model W and B that minimizes these errors. So again, in machine learning, when we have to first come up with the concept of an error, we have to find a way to measure errors in our models, first of all. And after that, we have to define an objective function. Given that error, how do we define all these functions based on this error over our data set, and decide what parameters we're going to minimize, for example. And sometimes some people, for example, decide to optimize everything, all the parameters in our model here. In some other cases, you'll see that maybe some people fix, for example, oh, I'm going to fix maybe the B, for example, beforehand, just to make it easier, and only optimize W's. For example, you find all kinds of things like that. So you have to first define an error function, and then define your loss function over data points, and then decide which parameters you're going to optimize in the model. So these are 3 key steps. We'll do for all the models exactly the same things. Does it make sense? So this optimization formulation is minimizing what we call the 0-1 loss, because this could be either a 0 or a 1, basically. That's why it's called 0-1. This indicator function gives us an output either 0 or 1. So minimizing a 0 loss function, we'll see shortly, it's actually not easy. It's actually quite difficult for several reasons. If you look closely here, so for example, on this particular plot, on the right side are the correct predictions. So what we're plotting on the x-axis is y times our predictions. So this in the bracket is our model prediction, basically. And if they have, again, if they're positive, it means the predictions are correct. If they're positive on the right side, then it means it is correct. If it's negative, it was incorrect. It had different opposite signs. So so the function exactly, the 0-1 loss looks like this. So it stays at 1. So you have a loss here. We have an error there, error, up until you have no more error, and you have 0 error. So so this is actually quite difficult to do. Do you know why? Why it's difficult to optimize it?
I think the derivative will be the same for the negative prediction, and apart from that, I think it is not continuous in one equation.
Yes, it has many problems. Yes. So the derivative is always the same. It's always so derivative is always 0 everywhere, and it doesn't exist in here at this particular point. The derivative does not exist because it is discontinuous. It only exists in the limits from both sides. Number 1. So when we have no derivative, like we have almost no idea whether we're making progress. That's why we need the derivatives that are. That's why we need to find derivatives, and derivatives that are meaningful, sort of, so that we can tell us that we're making progress in the optimization. And another problem this function has is also that it's not only it doesn't have derivative, but it's discontinuous. At this particular point, it's completely discontinuous. It's not smooth. It's not continuous. It's not easy at all. Um, yeah, and more. I mean, I'm not even talking about convexity and concavity, so all of that. But even against all these odds, actually, there's some work in the literature that people are trying. They found some ways to even optimize these kinds of functions. And we're not going. This is actually goes quite advanced. Like we're not going to go cover this in the course, but you can do things like you can define, for example, what's called a surrogate function, like a surrogate loss. It's like a different loss that kind of approximates this 0, 1 somehow. It's not exactly the same, but it maybe it for example they make it continuous here, or and it has like better behaved properties, and they found that if you optimize these surrogate losses, you still get the exact same optimal parameters, even if you change the loss function slightly. So these kinds of things people do, and there's also like other search types of methods, like you can kind of search through the parameter space with something more like sampling-based methods, for example, and you can still do something. But it's generally hard. It's hard to optimize a 0, 1 loss. That's the message. And some alternatives to optimizing it is, for example, if we also find an upper bound. And when people in machine learning talk about upper bound, it means that you have your loss function, which was like a 0, 1 loss or something else, and you find another function that is always above it for all the values, kind of. That's what it's called an upper bound. And what happens is that if you optimize the upper bound, if you always try to push the upper bound to be lower and lower and lower, you essentially constraining the actual function which lies beneath it, basically, to kind of also like maybe minimize. So essentially, that's how people have been optimizing all kinds of crazy functions that were otherwise hard to optimize. They define an upper bound instead, and then they optimize that. Yeah, I've said this already. Yeah. Does it make sense how the upper bound pushes the function down and down and literally kind of pushes the solution? No. No, it doesn't. So let me explain. So you have a particular function like this, for example. Like this would be like a loss function. And then you define an upper bound like something like this. This would be an upper bound. So this will be another function g, and this will be f. And you always know g is higher than f for all these points, for all the ranges. So when you optimize g, when you try to what happens that when you optimize g is going to push down on f basically, and basically you're gonna find the solution that by minimizing g, you're essentially kind of almost minimizing f, because for example g would have a minimum, let's say here, for example, and f always has to be below this minimum. So kind of by minimizing, I don't know if you can see here, but by finding a minimum in g, you're essentially pushing down on f.
What if the minimum of f is right in the middle here, that's under the maximum?
Yeah, you always have this problem. So yeah, so optimizing an upper bound does not guarantee that you're actually finding the minimum of f. It kind of...
We may be informed based on other things we might know about f.
But what it tells you at least is that the minimum of f is either here or below it, or below this point. So only if this one was actually going like below it, then you might have lost this one. But otherwise, it tells you that at least this is a reasonable enough solution, if that makes sense, kind of. Yeah,
Okay.
kind of. That's kind of the intuition. So maybe it's not the best example. Like you can, like let's say if this was our function and this was the upper bound, more like this. Maybe that's like a better way. So this is our function f, and this is g. So again, maybe this one is hard to optimize for various reasons. Like I don't know. Let's say this is a step function like this, or something else. and we kind of put an upper bound that is better behaved, continuous, and we kind of find a spot. So we hope that this minimum here would translate to a good minimum for f as well. That's the idea. A bit of intuition for now. We know this is getting quite theoretical. Like if you take a theoretical class in ML, you can we'll discuss a lot about upper bounds and stuff. Yes.
So the G has the same parameter as f.
Yes, it's the same parameter space. They lie in the same space. So if this is n-dimensional, this will be this exact same n dimensions. Yes. The key idea is that for all, like formally, again we're going to lesson formally for all x, g of x will be bigger than or equal to f of x. This is kind of how so for all x, g of x will be greater than or equal to f of x. This is how you define the upper bound, and it has to obey that property. And okay, so this is this is what we mean by upper bound here in the slides. It's a function that is always always at least as Look at this example. Actually, this is a another nice example. Look at these 4 loss functions: the 0, 1 loss, exponential, log, and hinge. So look how for the 0, 1 loss, which is this one, all the other losses are upper bounds to it. Basically, for all the x's in this range, for example, the hinge loss will always be greater than or equal to the 0, 1 loss. So it does obey the property. It's an upper bound. So then people say that, instead of optimize the 0, 1, we can optimize a hinge loss, which is easier. It's a bit better behaved. At least it's continuous. So at least it's continuous, and it doesn't have a derivative at 1, but at least it's continuous. So it's generally easier. And it gives sort of meaningful derivatives on this side when it goes down. And even, for example, the log loss and 0, 1 again are upper bounds, and all like even these are also even smooth. So does it make sense? So finally, a point I wanted to make is sort of like, why does it work to take a loss function and sum over all the data set and basically basically optimize this what we call the empirical risk. Why does it work to basically minimize the empirical risk when we sum losses over many data points? It's because from the law of large numbers, it's something that you can read more at home in statistics. And essentially, if you take many experiments from many samples from the same distribution, or do the same experiment many times, you will converge to a particular value always. Like when you take the mean, for example, of overall solutions. This is what the law of large number means. If I toss a coin many times, the expected number of heads will always be like a half of total number of heads. For example, like so if I keep tossing a coin, if I keep throwing a dice many times, I always see like roughly it will converge to these numbers will converge to. What is called on the left is called the empirical distribution in some other terms in what is called in statistics, and the thing on the right is called this is the actual distribution. It's the true distribution, and these always converge. If you take many samples, the empirical distribution always converges to the actual distribution, the true distribution, for example, like of the underlying model. If you take many samples, let me phrase it in a different way. This can also be phrased, for example, in terms of statistics, that this is, for example, in statistics, this is called an estimator, and you have an estimated given your sample is of the sample mean, for example, of the errors, and this will always converge to the expected value over this distribution, as long as as long as this is an unbiased estimator, and this is an unbiased estimator, it will always converge to the mean. So we're not covering a bit like in terms of statistics like this, biased and unbiased, but this is this can also be phrased like that, and it's also related a lot with what people call the central limit theorem in the statistics, where if you take the same that one is actually even more powerful, because if you take the same number of if you have a random variable and you take many IID instantiations of those random variables, their sum, so x1, you have x1, x2, xn, their sum will always converge to a Gaussian distribution, which is an even stronger result than this. But this is kind of you can kind of derive this from a central limit theorem in statistics. So anyway, I made several points here, but kind of I hope some of them made sense. But you can ask me more in the office hours. Do we have any questions? Does this make sense? Why this converges? Do you understand why the right-hand side is different from the left-hand side? This is expected value over our distribution of the data points of x's and y's. But this is a theoretical sort of like a construct. It's sort of saying if we had an infinite number of data points, this would be sort of like the mean of that. Is kind of and this, if you take a finite sample, this if you take many of them over time, this will converge to the sort of behavior when you have an infinite number of data points. Kind of, that's another way to understand it. Yes.
So
what is what?
Theta.
Oh yeah, theta are model parameters. So these are the parameters that we are optimizing for. So we will take theta are here. Here, theta are our model parameters. These are the parameters we're trying to estimate. Or theta here, for this particular example, is the slope of the model. Theta gives you the exact line, which line will actually fit the data. So here, theta would be just a slope, would be p in this case, the parameter p. Theta would just be made by p, and it gives you the slope of the line that will fit the data best. So because the whole point is that we're trying to estimate to find this line that is optimal. So what we do, we define loss functions over. We define a loss function like this over parameters theta, and then we minimize that, optimize that. We take the derivative with respect to theta of this loss function. We set it to 0. We solve it analytically, or we do gradient descent, and we keep taking gradients with respect to theta of this loss function. So theta is the key parameter we're trying to optimize. Any other questions? Okay, let's take an 8 to 10 minute break. I'll give you a longer break this time, and then we'll continue afterwards. Yeah.
So X is all the features, and Y are all the labels.
X are the features, and Y are the labels. Yes. So X would be something like. For a person is like, for example, let's say if you want to predict the person's credit score for a bank, for example, you're a bank and you try to like assess the credit score of someone. So you can, you do it based on like, X would be, for example, you would have like, your income, your, I don't know, salary, past history of paying on time, loans, stuff like that. So that will be all this information being X, will be your features. And from those you want to predict the credit score, someone's credit score.
What would be the label for that?
So it would be like a number, like, a score from 0 to 900, like, for example.
Okay.
So for each person. So that's Y.
Okay. So Y is the actual credit score.
It's actually credit score.
Okay.
Yeah.
And theta is trying to get to Y.
Theta is the parameters that here. So these are theta, but basically in this theta are the parameters that give you the model. So this would be the credit score. This would be your income, for example, like your salary, let's say. So So theta is what gives the line, kind of. It's like the slope of the line. Does it make sense? Because the whole thing is you're trying to find a model, find that line that predicts the credit score. So you can, yeah.
So for nonlinear models, I guess, are you trying to take the derivative as the one that goes to 0?
That on the left hand side? Yeah. So this is the visualization of the loss function. You see, this is the loss. This is what I call the loss, the cost of the loss over a parameter theta, for example, p. So, and we take a derivative at each point, so we try to set it to 0 when we solve it analytically, kind of. We right away we have this equation, and we set if this is 0, and we solve it. But with the SGD, you take steps up until you reach that point.
So I have another question. So as you're updating theta, and you're getting closer to 0. Does x become what is x? Because you can't just use the same input, can you? Because as you repeatedly
As theta gets to 0, or the derivative of theta, derivative of the cost. No, it's derivative of cost with respect to theta. More precisely, it's not. Yeah.
Professor, are we
yeah.
going to have a quiz thing?
Not today. Not
Okay,
today. That's why I gave a slightly longer break.
Okay, good, because I have to leave because I have to attend the lab.
Yeah. No, not today. We're not doing
Okay,
quiz
good.
today. Yeah.
Okay, thank you.
Yeah.
I have to tell you that.
Yeah. No worries.
Yeah.
Yeah. No worries. Yeah.
So I was thinking you had a simple example where x was 1, 2, and then y was 5, and theta
Yeah.
was 1, 1.
Yeah.
And
That
theta's
one.
trying to be 1, 2 is trying to get to 1, 2.
Exactly. So the 1, 2
Yeah.
would be like the optimal parameters of that particular solution. Yeah.
So as theta was 1, 1 turned to 1.1, 1.2, what is x then? Is it still 1, 2?
X is always so.
Because
X, I
would
know.
be 1, 1, 1, 2.
No, those are the parameters. So X are your data. This is always your data. Theta are the parameters. It's kind of like saying how do you transform. Theta is giving you what are the numbers you need to apply to transform X to transform your salary to predict your credit score. Your salary, your everything to. Yeah.
Maybe is a better way of thinking it. You're using all of the data.
All the data in X that we have.
Each time, and then that updates theta. And then use all the data that updates
Yes.
theta.
Yes.
all the
Yes.
data
Yes.
that
Yes.
updates
Yes. Yes.
theta.
Yes. Yes.
Okay,
Yes.
that makes more sense.
So, yeah. Although, so this is in general for a gradient descent, but the stochastic gradient descent just takes one data point. But you can do, but this is, you can do the same for all the data. You can take the whole data at once and do that update. That's also possible. You can only take chunks of it. It's called batch. The batch. So that's called batches. You can do all kinds of things. Yeah. There's some more actually. There's some reasons why you don't want to do the all data at once, because you can get stuck in the optimization. And we haven't gone. It gets a bit more like advanced, but like reason why you don't take local minima. So when you do stochastic, like you take one by one or in chunks, you can escape the local minimas. You can jump out of them.
Another machine learning course we did the evolutionary algorithm.
Yeah.
And that was a cool model to show how you can escape.
You can escape local minima. So it's the same thing if you take all the data at one go, you can get stuck and escape them. But we won't have time to go to like all the ins and outs. Yeah, but yeah.
I just submit my my homework
Yeah.
assignment, but it's kind of something weird. I typed my equations in LaTeX, but after I submitted it, have just missed some symbols.
Some
like
symbols.
This, EX, it just missed. Yeah,
E of X.
Yeah, I submit several times, but I still have these problems.
Got it.
Yeah.
Can you write a note to, like in here in the submission? Like, can you write like a message to say, "Oh, I had this problem"? Like,
Yeah, maybe I can
you can
write it next time. Yeah.
write or write to my TAs also, like and stuff. We'll have graders actually to grading these.
Okay.
So yeah.
So,
But so somehow I have to get to them. But so when I announced the graders, because I'm in the process of hiring them, so you can also contact them, also email them, so to tell them that, to make sure, yeah.
But I'm afraid it's not afraid the whole equations.
Okay, shall we continue? we will not have a quiz today, and we'll go straight into Perceptron, because I think there's a few things we have to discuss here, so we won't have time for a quiz. But I think it's a really interesting lecture. So this is quite a we'll talk about the Perceptron, which is an algorithm that was developed a long time ago in the 60s. So by a scientist called Frank Rosenblatt, and he was a cognitive scientist. So he initially started he's interested in mainly in cognition, and then kind of ended up building this learning algorithm and sort of implementing it on a machine, and it's a really interesting story. But let's get started through it. Before we start, I wanted to also say that if people on Zoom, feel free to ask me questions at any point and interrupt as well, because I'm trying to make it also with the Zoom a bit more interactive. So if anyone has any questions, do interrupt on Zoom also. Okay, so basically this is what is called the Mark I Perceptron machine that was basically implemented by a cognitive scientist called Rosenblatt, so back in the 60s, and this was a big, look at it, it was a big machine that was implementing a particular type of learning algorithm, and it had an array of photosensors, so they would kind of have some sensors to detect kind of objects, and kind of that were placed in front of them, signals from these objects, and they would pass through all these wires, and then that would do these linear operations we were just talking about, literally just doing linear operations, and these would this would be the output. So and this was him kind of going through these wires, and it's sort of this is early on in the history when AI started. Sort of people in the 60s, that's when sort of people started actually thinking about AI, how to do artificial intelligence, how to make machines to do smart things, and so on. And this was one approach, one type of algorithm that was kind of used back then, and it's sort of implemented on a really huge machine. And you have to take it a bit into context, because back then, of course, these machines and computers were not powerful enough, so they could only do really basic operations, and also work with really basic, super small data sets. So what we're doing, what we go through right now, is it will be quite a very simple learning algorithm, but at the same time it was quite important, because this is where this marks the start of neural networks research. Because the neural networks are kind of you can think of building Perceptron as literally because it's a really simple neural net. You can think of it like that, with only one neuron. So the Perceptron is an algorithm to learn a decision boundary, which is linear. So what we were discussing earlier, and so the goal is to learn so we have an unknown function f, an unknown model that takes for example inputs x and predicts a y. So this is a function f, and what we're trying to do is to learn it. So basically to learn an approximation that is that can approximate f as well as possible. And of course, f might, as always, f might not be linear. F might be non-linear. But with this, we're trying to approximate it with a linear model, basically. So right now, we're learning a different function g that approximates the true model f. So as inputs, we'll have a set of training pairs, x and y. So x is the same thing. X is a d-dimensional feature vector for each particular data point, and y is the label. And this is a classification task and not a regression task. So the label is discrete and categorical. And in particular, for the Perceptron, they do only binary labels. So again, y will be +1 or -1. It can be extended, but it's not obvious how to extend it, so we're not going to go through that. So and the hypothesis class, what we call the hypothesis class, is all these hyperplanes H that can linearly separate, or all these lines that can separate our data. And then we're trying to find what's the best such line or approximator of f. So sort of again the Perceptron it was really inspired by cognitive science and how neurons work, and basically we this was also a time back in the 40s to 60s where people started actually doing a lot of neuroscience research. It kind of started actually like studying neurons. There was the perceptron is also called like a McCollum-Pitts neuron. It's actually called like a neuron. So it's basically it has a lot of inspiration from neuroscience, and more precisely how it would work is for example you have a neuron in your brain, and it has an axon here. It has a synapses and dendrites, and each of these are dendrites and synapses at the very end, and this is an axon that's connected to other neurons. And this particular neuron, for example, it would have inputs. This neuron here, this body, would take inputs from these synapses, and then you can think of it as it would sum them together, for example, and sum them together and basically create. Well, in neuroscience, it's what was it called? It's called an electric impulse, no, an activation signal, something like that. And if this activation signal then can generate an impulse, and that can be spread to the axon to the other neurons. So this is almost the same idea. We in the perceptron, we essentially sum multiple inputs, x1, x2, and so on, xd, and we weight them by some weights. And then if the sum passes a particular threshold, then we send a signal. So sort of like we send an output, sort of like, and this is called like the activation function. We compare if this sum passes the threshold. So the prediction again will be a 1 or a 0 if we send a signal or if we don't send a signal. So the inspiration again, the idea of inspiration does come from neuroscience, and this will be the equation. So again, we sum all the inputs and do a weighted sum, weighted by W, and then we add a bias term, and then that will be our activation. So again, we spoke just now about linear boundaries and how an orthogonal vector W can give us a linear boundary, basically, that like a vector W can give us a boundary that is orthogonal to it. And again, it has all these equations. So this is the equation of that particular line. This will be the activation. So we set this to be equal to A. And again, like if A is bigger than 0, then I'll predict class 1. Otherwise, this is class 0. So this A would be our prediction or our output of doing this. And and one small difference from before. This is actually using a different standard here in Perceptron. So instead of doing minus wx minus b as in previous slides, this is doing wx plus b, but it's basically the same. It's just they're completely identifiable. You can always flip the sign of b to be the other one. It's just a different notation that is used, but it's the same thing. I don't want you to get confused. So how the perceptron predicts something is really simple. So again, it takes these biases. It takes a particular test instance x. So this is again a vector. It has all these weights and the bias, and does the sum, and it computes the activation, and then it returns a sign of this particular activation if it's a plus 1 or minus 1. This is simple. This is how you predict with the perceptron. So again, super simple. But then the key thing is, how do we train this model? How do we actually train to find the optimal weights and biases? And the broad idea, the really broad idea, is that we first initialize the model to some. So here by the model we mean the parameters W and B, and we initialize them to some value. For example, they could all be 0 or maybe non-negative. Or non-zero, but yeah, any sort of values. And then for every instance in the training set, one by one, we use the current W and B to predict a label. So we, as we see earlier, how to predict like that, we can use the current W and B. And if the predicted label is the same as the true label, then we do nothing. We don't change anything. And if they're different, we update our model, the weights and the biases, such that it will do better on this instance. But this is the general idea. So we've seen this, and we applied this again in other kinds of. And if you think about it, even stochastic gradient descent almost does this as well. Because when you take the derivative, for example, you're trying to move. If you're very close to the solution, the derivative will be 0. So you will do nothing. For example, you won't move too much. Whereas if you're very far away, the derivative is highly positive or highly negative, then you will move a lot. So So if you see, it's the same sort of spirit. And this is also, so this again, as in stochastic gradient descent, this is also taking one data point at a time. And it can also be seen as an instance of online learning. And online learning means where we don't take, our data keeps coming, basically. We have a continuous stream of data coming, for example, and then we can keep on updating it with the new data that comes. So we don't have a fixed, for example, like, training data. But this is, this is online learning, and it's doing it one by one step at a time. And it's also error-driven learning because we update only when we make an error. So again, these are concepts that will be used in a lot with many other models, not just Perceptron. So we only update the model parameters when we make errors. And this is the training algorithm. So we still have some time. So how does it work? So look a bit closer. So forget about these for now. Start from line 5. Look at line 5 or 4. So this side here. So for all data points, for all pairs of data points x and y in our data set, we take the inputs, we apply the weights and the bias, and this will be our prediction of one particular data point. So we apply the model, and this will be our prediction. We get an activation. If the sign of the activation is different than the sign of the true label, then we do an update, because that means we made an error. This is if we make an error, if the signs are different, then we do this update. And the update is that we take our weights and we add for each dimension in the weights, we add xd times y. So basically, this is y is the label of that particular data point, and xd is the coordinate. And we also add to the bias. We add to all bias. We add the sign of that particular data point. This is all we do in the perceptual learning. And of course, at the beginning, we initialize these weights and biases to 0. And we repeat this until convergence. This is how we train the perceptron, and how it was trained. So again, error-driven learning. We only update if there's an error, if we make a prediction error. This is when we make a prediction error, if this happens. Is it okay to check for y times a smaller than 0? What would happen if we do that? We have somebody? No? Oh, okay. Any ideas? What would happen if we don't have less than or equal to here, and we have just smaller than? Sorry? Was that again? Yeah. Almost. Not, what happens is that because we initialize everything to 0, for example, all the weights and biases to 0, all the activations in the first iteration will be 0, because we do 0 times x plus 0, so it'll be 0, and basically it will get stuck. The algorithm will get stuck, so it won't make any progress because everything will be 0 initially. So it would work if we do less than or equal to, but only if it should work. But you don't have to start with 0. You have to start with some non-zero values, like that's something like that. You have to be very careful. But otherwise, yeah, it's.
What if you just had, say, some of your weights, like half of them started at 0 and half of them didn't? That in this first iteration, some of them we're going to have changes in some development, but others, may not. And if we had used
I'm thinking if it's possible that those dimensions will get stuck or not.
So
but
yeah, right. They could, or maybe they could just get stuck in one direction. I don't know.
I think it might still not. It might still be okay because you sum over all the dimensions here in activations. haven't thought, but yeah, it's you get the idea. Yeah, it's, you can think about it more carefully. So let's see what is happening actually mathematically when we do a single update in the perceptron. First of all, does this make sense? Do you have any questions about this before we move on? Yeah?
I just don't understand the update view. I mean,
Why we do this? Yeah. Why? I have some graphs, some plots, some nice plots. I think it will answer your question soon, like in the next few slides. I have actually some plots for that. But we essentially trying to move. By doing this update, we're actually moving our vector, vector to be closer to those data points. You'll see kind of shortly, kind of like how, roughly the intuition. Any other questions? We'll get shortly. We'll see what happens with these updates. Why do we do exactly these updates? But at least you get this. This is when you make an error. This particular if statement. So let's look at now in detail at a single update on the perceptron. So we have an instance x and y, and we assume that y is a +1. So this is showing positive. And however, we see that our perceptron made a mistake. So let's say our activation was negative. So that we made a mistake. So what happens when we do the update? So this is what happens. So our activation. Our new activation will be a sum of the new weights times x plus the new bias after the update. The new weights are the old weights plus xi. So for each wi plus xi, the new bias is the old bias plus the sign, which is y, plus y, which is a +1. So that's why you get b +1 here. And if you rearrange this, you basically get wi times xi plus a b, and then you move these to the right. So you get the sum over all these x's +1. And if you look close to it now, these two terms were exactly the old activation. These were the exact activation from before. But now we add, so we have essentially, so the new activation that we have is literally the old activation plus xi squares +1. This is what happened. So what we do is that think of it like this: the old activation was negative, right? Because we made a mistake. The old activation was negative, but by now the new activation, well, after we did the update, will have some additional terms that will be always positive. So we're making the activation closer to being positive. Maybe it's not going to be positive after this update, but it's towards that direction basically. And if we do and if we do it a few more times, we might cross the threshold. So it will become positive. So this is the intuition. Yes.
You said the one inside the point was always y, right?
Yeah. Yeah, it's here. So b, you update to b plus y, because if the activation was negative, it has to be flipped. You have to flip the bias. But so these two rules. So b goes to b plus y, w goes to w plus y xd. So again, y is 1 in our case. So that's why. So the new activation is w plus y x, which is just 1 times x. So it's w plus x. Does this make sense? This? Yeah. So again, so the new activation will be closer towards 0. If it's not already positive, it will be closer to being positive. So this is roughly. So now in the last 5 minutes, so I wanted to show you. So this is roughly what is happening visually. So we have our orthogonal vector. This gives us the separation plane, the separation line. And for example, we have a data point that is misclassified. We have a misclassified instance. And what this does when we update is that it's sort of changing our vector to by adding this vector. Basically, we're literally adding that vector to from this data point to our original vector. So now the new vector W will change, will give us a different separation line, which is a green one now. And in this new separation line, the data point is now correctly classified. Yeah. So one thing to really note here is that these perceptrons, so this is again a bit of history, cannot learn nonlinear boundaries. So basically this is all it's a linear separation problem. So for some problems that are nonlinear, for example, the perceptron will not be able to fix them. So and there was a famous so when these things started, of course, people were very excited about like perceptrons and so on, and like how they could revolutionize and learn all these new things. And there was a book that was published by Marvin Minsky and Seymour Papers from MIT on perceptrons. So some years later down the line, so that's the book on the right. And they showed the key ideas. That they showed that for a simple function like XOR, the XOR function, which is this, for example, you have like those quadrants are positive, those two other opposites are negative. A perceptron cannot learn this function because this data is not linearly separable. There's no line that can separate. There's no straight line that can separate these easily. So it's just impossible. So because of this actually led to a huge reduce in funding for AI research back in the 60s, and led to an AI winter. And it took almost 20 years up until the 80s when the field picked up, like the connectionist field and so on, and studying these new nets and so on. So it took until the 80s to revive. But it's sort of like it's a very important algorithm because it was it sort of started the field of neural network research. So and that's why we're studying it, and I think it's important to understand it. So of course, another thing in practice to keep in mind when we train a perceptron is that the order of the training instances is important. So how we actually order those. And for example, the example of a bad ordering is when we take all the positive examples followed by all the negatives. In general, it's best if we reshuffle all the data, if we randomly reshuffle beforehand. And even after each iteration, we can do that. So again, the way we take these instances is important. For example, when we do this for loop. And the classifier again. So the margin of a sample is what we were talking about earlier. Is the distance from the classification boundary. So again, it's positive if it's if it's correctly classified, it's negative if it's incorrectly classified. So this is the margin from each data point to the classification boundary. These distances. And for the perceptron, this gives us this equation. So again, from the last time, this is the distance from the margin of the classifier. This is equal to m over w if we have a homogeneous representation. And we can and I think I'll stop here because we almost have 3 minutes left. But I'll take any questions if you have. Do you have any questions about all of this? Okay, so assignment 2 is out, and it's due on the 17th, so it's almost 2 weeks. So do start and let us know if you have any questions. Yeah.
Yeah. When I was submitting it, I kept having a lot of trouble getting it small enough, and I realized I think I forgot to submit the CSV file along with it. Is that all right, or should I?
The CSV file, that's fine. Should be
Okay.
fine. Yeah.
No,
Don't worry.
I was gonna do it in Monte, and I ran out of time
Don't
to
worry.
look
Don't
at
worry.
pictures.
Don't worry. Yeah. No, yeah. The greatest will have it. Yeah.
Next one's though.
Yeah.
Make sure to submit early.
Yeah.
Thank you.
Yeah. Hi. Yeah.
Where are you trying to exactly go with our W? Are you trying to match it with our X? Sorry. So here you are telling that we add these two vectors and it comes here inside this plane. But what is our end goal? Like we will keep iterating this, right?
Keep iterating. Yeah.
So where do we want to reach with W? Because in gradient descent, we know we want to come to the minima, and we will keep updating our weight.
There is some. So there is actually like some proofs in several articles back in the 60s and like like that kind of time that show that if certain conditions are met, the perceptron will always converge to a solution. So there is like a proof of that. But it's like we're not going through it in the course. But this proves that if you do this, this is the update. You understand the update. Those things prove that this will lead to eventually to a boundary that separates the data. And this is as long as the data was linearly separable to start with.
Yeah.
So as long as the data was linearly separable, like you will find a solution that separates them. There's other proofs on that. There's some series of papers in the 60s, but again,
Okay.
Kind
so
of,
it's kind of confusing here that we are actually adding W and plus X, right? So
yeah.
So how are we exactly making our W so that it would basically our idea is to our final Y should match our this W into XT, right? But this equation doesn't give that intuition, right? That we are trying to reach that point. Yes, that's what my.
But so you do add this vector. You add the XD. So. So you understand this makes sense that you're doing that, right?
Yeah.
This makes sense.
Yeah.
So what is the question then? Or
so if we update again, so basically we are these two will add, right? If it will come somewhere in between, it will keep updating, and at the end
that makes sense.
Are we reaching to the
I know
X
what you mean. I know, but as long as you have some other data points that are negative on the other side, they will also pull you kind of on the other side. They will those other points, because if you only have pluses, yes, you will come to the mean kind
data
of.
point, all the data points basically.
And it won't work. But if you have a set of minuses as well, they will also pull on that side. So have some. It's a balancing force kind of. That's why kind of the intuition comes.
I have one more question. This one.
Yeah.
This is perceptron. This one. So this is not a straight line, right? This is plane. It's a plane, right? Because this W1, W2, right? And we have basically we have two dimension, right? And